Okay, let's start. Last week, we defined elliptic functions as doubly periodic homomorphic functions. And proved several important theorems. Today, we construct a very important example of an elliptic function explicitly. That is Weierstrass P function. Okay, until we have already defined the Weierstrass function as the inverse function of such an elliptic integral, but we construct it very concretely, explicitly. It is possible because Weierstrass P function is one of the simplest elliptic functions. What do I mean by simplest? Well, recall that if an elliptic function is homomorphic, then it's very trivial, just a constant. Of course, constant functions are elliptic functions, but no other entire elliptic function exists. And we have also proved that an elliptic function of order 1, namely an elliptic function which has only one simple pole, does not exist. Well, in principle, it's by the residue theorem. So the simplest possible non-trivial elliptic function should have two poles in a parallelogram, in period parallelogram, with multiplicity, namely, it should have one double pole or two simple poles. And the P function is the first example. It has one double pole, as we see, and the Jacobi's SN function is the second example, which has two simple poles in the period parallelogram. We shall see it well in 3 weeks, I think. Okay, so today we construct this P function, Weierstrass P function, by a series. Well, so this is the construction, and well, as before, we choose two complex numbers which span a parallelogram, and as usual, the lattice spanned by these two numbers are easily noted by gamma. And we construct a elliptic function which has double poles at the lattice points of gamma. So, well, let's expand such an elliptic function at a lattice point, omega 1 plus m2 omega 2. Then, if an elliptic function has a pole over the n at these lattice points, the Roland expansion should have such a form. Well, we don't know what are they, but anyway, at any M1 and M2, see this coefficient should be common, and n should be the same for any lattice point. So the simplest candidate of such an elliptic function is just sum up this term. By ignoring such a remaining terms. Then, well, if this series makes sense, then it should be an elliptic function, named doubly periodic function with poles over the n. And indeed, such a series does define an elliptic function when n is larger than 3. Namely, well, exact statement is as follows. First, since this definition is a series, we need convergence. And actually, this series converges in a very nice way, namely absolutely and uniformly on any compact set in the complex plane except at lattice points. Of course, we have to exclude lattice points because each term diverges explicit. And well, yeah, it defines an elliptic function over the n. And moreover, it has a parity. Namely, if this index n is even, then it is an even function. And if n is odd, then it is an odd function. The proof is quite standard by the M-test, by stress M-test. Let's assume that K is some compact set which avoids lattice points. And since compact set in a complex plane is, yeah, you know it already in the course of mathematical analysis in the first year. A compact set in Euclidean space should be bounded and closed. So there exists a closed disk which contains this compact set as a subset. So let's prove absolute and uniform convergence on this disk, which includes K. And if it is proved, then we, of course, on the subset K, it should converge absolutely and uniformly. And moreover, we omit several finite terms, which corresponds to lattice points in a larger circle. This is where K sits. There is another. Circle. And we pick up lattice points outside of this larger circle, larger disk, and sum up all these terms. Of course, if n is recovered by adding such finitely many terms. So this omission of these terms does not affect convergence. Why we should exclude such finite terms? Because if the lattice point is outside of this larger disk and U sits in this smaller disk, here it's U and here it's then it is easy to prove that such quantity is bounded. You see that such an ratio of U and omega is probably less than 1/2 or something like that. We don't need exact estimate, but anyway. And therefore, we have such an estimate. And since each term of this series is a product of such a function and this constant, we have only to estimate this series. We want to estimate this part, this series, and this is equal to something so. This, and this part is less than m, so it is less than this. And we can prove that such a sum converges when n is not less than 3. What does this mean? This means that this series converges on this disk dr absolutely because we take absolute value, and uniformly because this part does not depend on u. And yeah, this is the Weierstrass test. And if such a yeah, so and each summand, which means u minus omega, such a term is of course holomorphic. Therefore, this Fn is a absolutely and uniformly convergent series of holomorphic functions, which is homomorphic because of Weierstrass theorem on such homomorphicity. So it is enough to prove that such a series converges. Well, it is not difficult if we look at the structure of the lattice. So this is the smallest part of the lattice. This is omega 1 and this is omega 2. And of course, there is some small disk inside. We can draw a circle inside this parallelogram. Then, if we multiply everything k times, then we have some parallelogram with many vertices with many lattice points with such vertices. And if lattice point, if a lattice point is on this parallelogram, PK, then well, it has the absolute value larger than K times R. R is this small circle, the radius of this small circle. And let's count how many points on this parallelogram. For example, on P2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 15, 16. And so on this parallelogram, there are 20, there should be 24. Well, yeah. Yeah. And so anyway, there are 8 times K at this point on each parallelogram. Therefore, this sum can be computed in this way. First sum over the parallelogram, and then I vary the size of parallelogram. And by this estimate, we have such an estimate, which means this. And such a series converges when n is greater than 3. Namely, this exponent is not less than 2, then it converges. So that's proof of the convergence and homomorphicity of this function Fn. And since each term has a pole over order n at omega, and everywhere else it is homomorphic. Therefore, we have this statement. Well, this has been proved. And it is an elliptic function, namely it is a periodic, doubly periodic function. Well, this is almost obvious from the construction, because for example, if we shift the variable u by omega 1, then we have such an expression. And by shifting omega by omega 1, then we have a one-to-one correspondence between gammas, the lattices, and so this is again f of u. So the periodicity is almost evident from the construction. And the parity can be proved in a similar way. I mean, let's consider Fn of minus u, which is this. And let's change the variable of summation by with minus omega. And we change the sign, then we have such a fact. And this part gives Fn again. So we have such a parity. You see that. Fine, we have constructed actually a series of elliptic functions by this. The point or the problem with this construction is that we have constructed third poles and higher order poles, but not double pole. We cannot construct the elliptic function with double poles only because this series diverges by this way. What should we do? Well, let's make use of one of these FNs and construct Weierstrass function in this way. And well, we are now going to prove that this series does converge absolutely and uniformly, except at lattice points on any compact set. Sorry, and this is a neighbor function with all poles of order 2. Well, probably this is obvious from this expression, but convergence is still to be proved. And well, yeah, I have already mentioned many terms, but this is the definition of Weierstrass P function by a series. Now, let's prove this. And well, yeah, the point is that we already know the convergence and the meromorphism of F3. And this has third order pole. We want double pole. What should we do? We can integrate this function to this. Let's do that. Well, the first term is somewhat problematic. Namely, this term is a little bit problematic. So let's exclude that and integrate it, which means this. And let's change the order of summation and integration, which is possible because we know that this summation is uniformly convergent. And well, this integral can be computed easily. At least you should be able to compute such integrals easily, and gives this part. With some constants. So, well, since we have obtained this part as an integral, this expression can be written in this way. And this is a meromorphic function. The integrand is meromorphic function. So this part is, of course, meromorphic. Well, this is, of course, meromorphic function. So it is proof that this series gives an meromorphic function, and the poles are at gamma. Well, this has a pole at 0. Each term of this has a pole at 1. Okay, so this is the meromorphicity of this P, and the point is that derivative of this P function is just F3 essentially with constant minus 2. You see, if we differentiate this integral, then we have such a function, and from this part we have this, and so they cancel, and we have minus 2 times F3. So we want to prove the double periodicity, but before that, let's prove the evenness parity. That P of minus U is equal to P of U. This can be proved again by changing the integration, summation value. Or probably that is, we don't have to trace details. And using this parity, we can prove the periodicity. First, recall that we have a negative function F3, and the P prime is minus 2 F3. So P prime, we have already proven that P prime is an empty function. By integrating these relations, we have such a periodicity. Well, better to say case periodicity, because we may have some additional constants. But these additional constants actually vanish because, well, let's put minus omega 1 or omega 2 over 2. Then this becomes omega I over 2. And of course, U is just minus omega 2. And the Ci, these constants are difference of them, but we know that they are equal. We have already proved. So these additional constants are actually zero, which proves that P has periods omega 1 and omega 2. So that's the proof of the W periodicity. And this construction gives the simplest elliptic function explicitly. Well, there are many good properties of this Weierstrass function. For example, the Laurent expansion at the origin can be computed explicitly because we have very explicit construction. Well, in the singular part, except for singular part, we have such summation. Therefore, by Taylor's formula, we have this formula, and this is not difficult to compute. Well, we can neglect this constant because we take derivatives. And by computing this explicitly, we have sum over lattice points of such terms with coefficient. Well, so these series give coefficients of this expansion. And by convention, such series with some strange coefficients are named G2 and G3. What does this mean? This means that P has such an expansion. And for the moment, let's neglect the higher order terms. And by differentiating it, we have such an expansion.